Patient's introduction. Welcome to this presentation on fast learning robots, the generative AI revolution in robotics. Traditionally, training robots has been a labor-intensive and time-consuming process. However, with the rise of generative AI, robots can now learn rapidly, shifting from explicit programming to learning through examples. This transformation significantly reduces training time, unlocking new possibilities across industries. The traditional robotics learning challenge. Conventional robotics training relies on hard-coded programming, physical demonstrations, and simulation-based learning. These methods are slow, require extensive expertise, and struggle to adapt to new environments. Additionally, transferring learned skills between different robots is difficult, limiting their real-world application. The generative AI advantage. Generative AI revolutionizes robotics by leveraging large language models, vision language models, and diffusion-based planning. These models enable robots to understand natural language instructions, interpret visual data, and generate precise motion trajectories. The result? Fast adaptation, improved generalization, and seamless skill transfer. How generative AI enables fast learning. With generative AI, robots use language as a universal interface, translating natural language commands into executable actions. By integrating multimodal learning, combining visual demonstrations with verbal instructions, robots can understand and replicate human behavior. Additionally, knowledge transfer from adjacent domains allows robots to apply common sense reasoning to new situations. Breakthrough technologies. Key advancements include vision language action models like RTX, RT2, and PALM-E, as well as diffusion-based planning frameworks like Unisim. These technologies enable robots to autonomously plan and execute tasks with minimal human intervention, dramatically reducing the learning curve. Case studies. Minutes, not months. In industrial manufacturing, generative AI reduces training times from weeks to mere minutes. For example, a robotic assembly task that previously took 3 weeks to program can now be trained in just 15 minutes using natural language and visual demonstrations. Similarly, warehouse automation benefits from real-time adaptation, eliminating the need for extensive fine-tuning. Real-world applications. Generative AI-powered robots are revolutionizing industries. In manufacturing, they enable adaptive assembly lines. In healthcare, they assist with patient-specific surgeries and personalized care. In agriculture, they optimize harvesting based on environmental conditions. And in logistics, they streamline warehouse operations and last-mile delivery. Technical foundations. At the core of this revolution are foundation models trained on massive datasets of human demonstrations, robot trajectories, and real-world interactions. Multimodal representations allow seamless translation between language, vision, and action, while transfer learning ensures robots can adapt to new tasks efficiently. The learning process transformation. Traditional robotic training follows a rigid pipeline requiring extensive coding, testing, and debugging. In contrast, generative AI enables a streamlined approach. Users simply describe tasks in natural language, optionally provide visual examples, and the robot autonomously processes and executes the task. Current limitations and challenges. Despite these advancements, challenges remain. Ensuring safety, bridging the gap between simulation and reality, managing computational demands, and improving explainability are ongoing research areas. Addressing these challenges is critical to making AI-driven robotics more reliable and scalable. Emerging research directions. The future of AI-driven robotics lies in self-supervised learning, where robots teach themselves through exploration. Open vocabulary robotics will allow them to understand arbitrary object descriptions, while collaborative learning enables robots to share knowledge across distributed systems. Advancements in causal understanding will further refine robotic decision-making. Implications for industry. This transformation has profound economic implications, reducing deployment times and enhancing ROI for robotics investments. The workforce will shift from programming robots to instructing them in natural language, making automation more accessible. Additionally, robotics as a service models could democratize access to advanced robotic capabilities. Future outlook. In the next 1 to 2 years, we will see commercial deployment of fast-learning robotic systems. Within 3 to 5 years, general-purpose robots will acquire skills across multiple domains. In the long term, robots will continuously learn from experience, communicate naturally with humans, and autonomously improve their capabilities. Conclusion: generative AI is redefining robotics, accelerating deployment timelines, and making automation more adaptable than ever before. By shifting from explicit programming to natural instruction, AI-driven robotics is democratizing access to cutting-edge capabilities. We stand at the dawn of a new era in human-robot collaboration. Q&A. This concludes the presentation. Thank you for your time. I'd be happy to take any questions